Let us continue our discussion on heat exchangers. Today I will explain how to derive an expression for log mean temperature difference for a counterflow heat exchanger and later solve a numerical example on counterflow heat exchanger. In the previous class we studied log mean temperature difference and its significance. Let us derive an expression for LMTD for a counterflow heat exchanger. Now the figure shows fluid flowing through a counterflow heat exchanger. One of the fluid is flowing through the inner tube. Let us say that is hot fluid is flowing through the inner pipe and cold fluid is flowing through the annular space and it is flowing in the reverse direction. The figure also shows the temperature variation for the fluid along the length of the heat exchanger. So here it shows the temperature, y-axis shows the temperature and x-axis shows the length of the heat exchanger. So along the length, the temperature variation for both the fluids are plotted here. So for hot fluid, the temperature varies from Thi to Th0, and the cold fluid is entering on the other end of the heat exchanger, and cold fluid enters at Tci and it exits at Tc0. Let us consider a differential length of the heat exchanger at a distance x from the left end. Now the temperature difference, that is the difference between the hot fluid temperature and cold fluid temperature, that is represented by theta. At any distance x, the temperature difference between hot and cold fluid is represented by theta. So the temperature difference at the inlet, you can say that inlet is left side of the heat exchanger. We will represent the temperature difference as theta I, and in this case for counterflow heat exchanger it is Thi minus Tc0. Whereas for a parallel flow heat exchanger it was Thi minus Tca. The cold fluid was entering at the same side and the difference at the inlet was Thi minus Tca for a parallel flow heat exchanger. For a counterflow heat exchanger it is Thi minus Tc0 and theta naught is at the exit, at the outlet it is Th0 minus Tci. Now the heat lost by hot fluid in the differential length. Let us take the differential length and the heat is lost by hot fluid from the inside a tube. Hot fluid is flowing inside, from the inside tube heat is flowing to the annular space where the cold fluid is flowing. So the heat is flowing from inside to the annular space. So the heat lost by hot fluid is equal to the heat gained by the cold fluid, and the same amount of heat is crossing the boundary of the wall of this inner pipe. So in this differential length, the differential quantity of heat lost by hot fluid is equal to the differential quantity of heat gained by cold fluid, and that same heat transfer has to cross the boundary of the pipe. So we can equate all the three quantities. So we will separately write down those quantities. The heat lost by hot fluid in the differential length as minus Ch dTh. C is a heat capacity of hot fluid, that is mHCph of hot fluid, into dTh is the differential temperature change for the hot fluid in that differential length. So from here to here, so in the differential length you are taking this differential element. For the differential element, the differential change in temperature, that is final temperature at the end of the element, the temperature, minus at the starting point of the element, the temperature, the difference, final minus initial, that is dTh, and that dTh is negative. So this dTh is negative for the hot fluid. So to make the quantity positive, I introduced a negative sign. So this will give the heat lost by hot fluid in that differential length. Now similarly you can find out the heat gained by the cold fluid in the differential length. Now the cold fluid, if you take, it is flowing in the reverse direction, but when you consider the element, at the end of the element the temperature of the cold fluid is less compared to the starting point of that element, that is higher. So the differential change in temperature for the cold fluid, it is final minus initial, that is going to be again negative. So dTc is also negative. So dTc is final temperature at the end of the element, the temperature of cold fluid, minus starting point of that element, the temperature. So the difference is negative. So dTc is also negative. So to make that quantity positive, this minus sign is introduced. So minus Cc, Cc is Cpc, and that is heat capacity of cold fluid into differential change in temperature of cold fluid, that will give the heat gained by cold fluid. So minus Cc dTc gives the heat gained by cold fluid in the differential length. Now the same amount of heat has to cross the boundary. Now you can express the heat transfer, when this is a combined mode of heat transfer, it involves convection, conduction, and again convection from the outer surface of this tube. So you can express the heat transfer coefficient by U, and U into area into the temperature difference will give the heat transfer. So overall heat transfer coefficient into area into temperature difference will give the heat transfer. Now in this case, area is differential area. For this element, the area you should take, that is differential area dA, and temperature difference here is theta between the hot and cold fluid, and that temperature difference can be taken more or less constant, because the variation in this theta is going to be negligibly small in this differential length. Variation coming for theta in the differential length can be neglected, and you can take the heat crossing the boundary as U dA theta. Now all the three quantities are equal, and you can equate that three quantities. So heat lost by hot fluid is equal to heat gained by cold fluid and heat crossing the boundary of the heat exchanger, and this is all happens in the differential length. So you can write the differential quantity of heat transferred in the differential length dq as minus ch dth is equal to minus cc dtc is equal to u dA theta. Now the temperature difference, as all of you know, temperature difference at a distance x is theta is Th minus Tc. Now if you differentiate, you get d theta is equal to dTh minus dTc. Now let us replace dTh and dTc from the equation 1, that is a previous slide. dTh is u dA theta by minus Ch, and dTc will get u dA theta by minus Cc. So both quantities, dTh is u dA theta by minus Ch, and dTc is u dA theta by minus Cc. So you can replace dTh minus u dA theta by Ch and dTc minus u dA theta by Cc. So minus of minus, it will make plus. Now you can take minus u dA theta outside, so you get 1 by Ch here, and minus u dA theta is taken outside, so you get minus 1 by Cc. So you are getting d theta as minus u dA theta into 1 by Ch minus 1 by Cc. So theta is taken to the left hand side, you can write it as d theta by theta is equal to minus u dA into 1 by Ch minus 1 by Cc. Now integrating and applying the limits, integral from inlet to outlet d theta by theta is equal to integral from inlet to outlet minus u dA into 1 by Ch minus 1 by Cc. Now integration of 1 by theta will give log theta, and applying the limits you get log theta naught minus log theta I, which can be written as log theta naught by theta I. This is a natural logarithm, or you can use log to the base e or ln. So it's equal to integration of this quantity is u is overall heat transfer coefficient. Let us assume that it's a constant, and assuming that heat capacities are not changing, or specific heats of both the fluids are not changing, and mass flow rates also remains constant, Ch and Cc remains constant along the length of the heat exchanger. You can take these things outside. So minus u into 1 by Ch minus 1 by Cc can be taken outside, and you get integral of dA. dA is a differential area, and integrate from inlet to outlet. You are considering, or you are summing up all such differential areas, which will give the total area of the heat exchanger. So integration of dA will give total area. So you will get the equation log theta naught by theta is equal to minus ua into 1 by Ch minus 1 by Cc. Now also we know that total heat transfer in a heat exchanger is Q is equal to Ch into the temperature change. Ch is heat capacity of hot fluid into temperature change for hot fluid, and also it's equal to heat capacity of cold fluid into temperature change for cold fluid from inlet to outlet. So in the total heat exchanger, what is the total temperature change? And again, this is a total temperature change in the entire length of the heat exchanger. So that is a total heat transfer. Earlier we have discussed the differential quantity of heat lost in the differential element. Now this is a total heat transfer in the entire length of the heat exchanger, that is also equal to UA into mean temperature difference or log mean temperature difference. Now you can get 1 by Ch from this. 1 by Ch is Thi minus Th naught by Q. So you can replace 1 by Ch, and also 1 by Cc from this. Q is equal to this equation. You can write 1 by Cc as Tc naught minus Tci by Q. So 1 by Cc you can replace as Tc naught minus Tci by Q, and 1 by Ch you can replace as Thi minus Th naught by Q. So that replacement is done here. So you can also see that the heat lost by hot fluid is Thi minus Th0 into Ch. That is Q. Total heat lost in the by hot fluid in the heat exchanger, Q is equal to Ch into Thi minus Th0. So you can write 1 by Ch as Thi minus Th0 by Q. Similarly, Q is Cc into Tc0 minus Tca. So 1 by Cc is equal to Tc0 minus Tca by Q. That replacement we have done. Now you can rearrange this here in the numerator. Thi minus Tc0. Thi minus of Tc0. So that is group. These temperatures are group. Thi and Tc0 is group. And minus Th0 plus Tca. So if you take minus outside, minus of Th0 minus Tci. Okay, minus of minus is plus. Here also minus of minus plus. So minus Th0 plus Tci. So minus when you take it outside, Th0 minus Tci. So what is Thi minus Tc0 is? It is a temperature difference at the inlet. This is the inlet of the heat exchanger. Temperature, that is the left end of the heat exchanger. Temperature difference is theta I. Thi minus Tc0 is theta I, and Th0 minus Tci is theta naught. So you can replace Thi minus Tc0 as theta I and Th0 minus Tci as theta naught. So log theta naught by theta I is equal to minus Ua into theta I minus theta naught by Q. Or you can rearrange this. Q is equal to minus Ua into theta I minus theta naught divided by log theta naught by theta I. Minus I am taking inside. So log theta naught by theta I minus log theta naught by theta I. Log theta naught by theta I is log theta naught minus log theta I. Once you multiply by minus sign, becomes log theta I minus log theta naught. That can be written as log theta I by theta naught. So minus of log theta naught by theta I replaced by log theta I by theta naught. So this part is log mean temperature difference. You can compare with the equation which you have written here. No, the total heat transfer is Ua into mean temperature difference. Our intention was to find out the log mean temperature difference or average temperature difference in the heat exchanger. So comparing with this equation, you can conclude that this part is mean temperature difference, and this mean temperature difference has got a logarithmic term in it, so it is called log mean temperature difference. This part can be written as LMTD. So LMTD is theta I minus theta naught by log theta I by theta naught. I just log to the base e, you can also write it as Lm. Now let us work out an example problem. Engine oil has to be cooled from 80 degrees centigrade to 50 degrees centigrade using a single pass counterflow concentric tube heat exchanger with cooling water available at 20 degrees centigrade. Water flows through inside tube of diameter 25 mm at a rate of 0.08 kg per second, and oil flows through the annular space at a rate of 0.16 kg per second. The heat transfer coefficient for the water side and oil side are 1000 watts per meter square Kelvin and 80 watts per meter square Kelvin respectively. The fouling factors on both water side and oil side are 0.0008 meter square Kelvin per watt. Neglecting the tube wall resistance, calculate the tube length required. Take Cp of water as 4180 joules per kilogram Kelvin and corresponding value for oil 2090 joules per kilogram Kelvin. So the purpose of this heat exchanger is to cool engine oil from 80 degrees centigrade to 50 degrees centigrade. So using water available at 20 degrees centigrade. So this is a hot fluid and its inlet temperature is 80 degrees centigrade and outlet temperature is 50 degrees centigrade. And this is a cold fluid and its inlet temperature is 20 degrees centigrade. So you have Thi 80 degrees centigrade, Th0 50 degrees centigrade, this is Tci 20 degrees centigrade. Also we know that it's a counterflow heat exchanger. Diameter of the tube is given 25 mm and water flow rate, that is cold fluid flow rate, Mc 0.08 kg per second and Mh 0.16 kg per second. And you know that heat transfer coefficient on water side as well as oil side. Water side it is, that is Hi inside. Water is flowing inside 1000 watts per meter square Kelvin and outside H0 is 80 watts per meter square Kelvin. And also the fouling factors on both inside and outside, and it is fouling factor that is for a unit area fouling resistance is given 0.008 meter square Kelvin per watt, and Cp values of both the fluids are given. Now we have to calculate the tube length. So THA, this data is tabulated here. THA, TH0, TCA, mass flow rate of cold fluid, hot fluid, CP of cold fluid and CP of hot fluid, inside heat transfer coefficient, outside heat transfer coefficient, inside the fouling factor and outside fouling factor. Now finally you have to find out the length of the heat exchanger tube. We know that heat lost by hot fluid is mH Cph into THI minus TH0. We know that mass flow rate of hot fluid and Cp value of hot fluid, which is oil here, and THI is also known 80 and TH0 is 50. So you will get the total heat lost by hot fluid as 10,032 watts. And the same amount of heat is gained by cold fluid, assuming that there is no heat lost. Whatever heat lost by hot fluid is gained by cold fluid. So Q is equal to mccpc into Tc0 minus Tca. Mass flow rate of cold fluid is 0.08 kilogram per second. Specific heat of water is 4180, and Tc0 minus Tca inlet temperature we know it's 20 degrees centigrade, and it's equated to the heat lost by hot fluid. From that you can solve outlet temperature of cold fluid as 50 degrees centigrade. So now all the four temperatures are known. Both the fluids inlet temperatures are known, outlet temperatures are known. Now you can find out theta I and theta naught, that is temperature difference at the inlet and temperature difference at the outlet. Since it is a counterflow heat exchanger, temperature difference at the inlet is Thi minus Tc0. So Thi minus Tc0, that is theta I. Thi, we know hot fluid is enters at 80 degrees centigrade, and the cold fluid, we have seen that cold fluid water is exiting at 50 degrees centigrade. So you get the difference as 30 degrees centigrade. Theta naught is the temperature difference at the exit. Theta naught is Th0 minus Tca. So substituting for Th0 50 and Tca is 20, you get 30 degrees centigrade. So both theta and theta naught we are getting same. So that means this difference 30, and here also the difference is 30. So if you try to apply LMTD equation is theta I minus theta naught, that will give 0, and denominator log theta I by theta naught, that is log 30 by 30, and that will give log 1, and that also gives 0. So 0 by 0, which is undefined. So if you try to use LMTD equation for such special case, this is a special case. Always we will not get the same temperature difference at the inlet and outlet. This is a very rare case where you got both the difference same. Since the temperature difference at the inlet and outlet are same, LMTD can be taken as 30 degrees centigrade. So in such situations, you can also use, instead of going for LMTD, when theta and theta naught are same or when they are very close, you can go for AMTD, which is known as arithmetic mean temperature difference. Instead of going for a log mean temperature difference, you can just go for a average, just mere average. Add both, divide by 2. 30 plus 30 by 2, you get 30. Suppose its difference is also very small. Say suppose it's 31 and 30. 31 plus 30 by 2, you get 30.5. And if you use LMTD equation also, you get more or less same value or very close to that. So when theta and theta naught, if they are very close, instead of going for LMTD equation, you can even use AMTD. So in this particular case, when theta and theta naught are same, you can take these values 30 itself as LMTD, because the mean temperature difference, LMTD means log mean temperature difference. When the inlet and outlet, the temperature difference are same, it is going to be almost same everywhere, and the mean temperature difference everywhere, it is having almost constant temperature difference, and that difference itself can be taken as a mean temperature difference. Okay, so we got LMTD as 30 degrees centigrade. Now you have to calculate the overall heat transfer coefficient. We know that the equation for overall heat transfer coefficient, here areas are not given, so area ratios are 1. So here 1 by u, I have not differentiated ui or u0. So area ratios is 1, a by a0 or a0 by a, it's 1, and also there is no resistance for the tube wall, so it's not added. Conduction resistance for the tube wall is not added. So you have only inside heat transfer coefficient, outside heat transfer coefficient, and fouling resistances. So from the equation for overall heat transfer coefficient, you can reduce to 1 by HA plus R of I plus R of naught plus 1 by H0. So substituting for HA and H0 and fouling factors. So HA is 1000, fouling resistance are 0.0008 meter square Kelvin per watt. The same for outside fouling resistance also. Plus 1 by H0 is 80 watts per meter square Kelvin. So you can solve overall heat transfer coefficient and get the value as 66.225 watts per meter square Kelvin. So overall heat transfer coefficient is 66.225 watts per meter square Kelvin. Now we know that Q is equal to, or total heat transfer is Q is equal to UA into LMTD. U we got, and Q earlier we found out 10,032 watts, and log mean temperature difference also we got it as 30. Log mean or average or whatever temperature difference existing in the heat exchanger is 30. So from this you will get the area of the heat exchanger. So area of the heat exchanger you can solve it as 5.049 meters square. So much area of heat exchanger is required to reduce the oil temperature from 80 degrees centigrade to 50 degrees centigrade. Now once the area is known, you can calculate the length of the tube required. Since the diameter of the tube is known, the surface area, the area through which the heat flows is known for a tube wall, the surface area is given by pi dl. So the area can be equated to pi dl. So pi into your diameter is given as 25 mm, so it is 0.025 meter into length. So length you are getting as 64.286 meter. So much length is required, 64.286 meter length is required to cool oil from 80 degrees centigrade to 50 degrees centigrade. Thank you for watching.